Well, hello, everybody. This is Jason Brownell from Polyfuze Graphics Corporation, and doing things a little bit different here. Good morning, good afternoon, or good evening, depending on where you're tuning in from. Have all sorts of stuff to go over today. I'm excited to get into it with everybody. Not going to have a moderator today, and I'm just going to cover a lot of information. So, again, thank you for joining me. Let me get something on the stage here. Okay, I'm going to go ahead and shut my camera off. That way you can kind of maximize the screen and see what we're talking about here. Let's see. I don't think I can turn the camera off without losing my voice. So bear with me. Um, Again, we're going to be going over not only the basics of polymer fusion labeling, but also how to set up equipment and kind of from working with photo eyes, working with fixtures, all sorts of things we're going to cover today. So the basics, right? We really hang our hat at the end of the day on working with durable goods. We're not going to be a good solution for necessarily a disposable item or something that has a real short lifespan. We at the end of the day hang our hat on items that 10, 15 years in the field that they need to have labeling. um, but it can be a challenge working with olefin materials. So we are very much a niche company in that we're working with the olefin family. So this is going to include all of your polyethylenes, whether it's a low density, high density, ultra high molecular weight. This is also going to include all of your polypropylenes, even if it's filled materials like glass filled polypropylene or talc filled polypropylene. And then we also get into soft touch materials like TPV, for example. Again, there's enough olefin content in there that we can fuse into it beautifully. But olefin materials have a challenge with labeling, and I'm sure most of the viewers that are on this right now understand this. And that is number one, low surface energy materials. In order for adhesive technologies to try to adhere, the higher the surface energy, the better. And again, we're not adhering to anything and we're not sticking to anything. And I'll explain more on that here in a moment. But if we look at one way to calculate the surface energy of material is with using dynes per centimeter. And when you look at like stainless steel and aluminum, for example, uh, these are real high surface energy materials. And then you get down to polyethylene and polypropylene, they're down around 30, where Teflon is coming in at 18, where we coat our cookware with it so nothing sticks to it, right? So again, it's a very low surface energy material. Nothing wants to stick well to it. It is also, if it's getting hot and then cold, it's constantly expanding and contracting. And so that can cause delamination. And then lastly, olefin materials um, will oftentimes outgas. In fact, a lot of times I'll go into a manufacturing facility and I'll see a staging area set aside where they are allowing things to off gas. Um, in order to understand our technology, I do kind of want to go over um, some other methods for labeling plastic. First up is just a good old fashioned sticker. And again, since you are working with a material that nothing wants to stick well to long term, stickers can have challenges and issues with olefinic material, and you end up with defects like you're seeing here, where it's delaminating off the surface. Next up would be hot stamp foil. And to this, I would include pad printing, screen printing as well, and then of course hot stamping. But again, when you look at it, you're taking an ink and an adhesive and trying to make it stick to a material nothing wants to stick well to long term. So you end up, with the defects like you're seeing here on the screen now, where it's just coming off the surface of the plastic. Next up, we have heat transfer. Heat transfer, typically, if you look at the construction of a heat transfer, you got clear coat followed by a layer of ink, then an adhesive layer. Again, that adhesive is a challenge because nothing wants to stick to these materials well long term. So you end up with the kind of defects that you're seeing on the screen now. And then lastly, for injection molding, you have in mold labeling, which the substrate itself that the inks are printed on does a really good job at um, mechanically bonding to the surface of the plastic. The trouble is the clear coat and the ink. If the clear coat breaks down, that exposes the ink, then the ink goes away, and you're left kind of with what you're seeing on the screen now, where you've got a substrate, but the ink is coming off. And so that brings us to the polymer fusion technology, which we are known for. And this slide kind of tells it all. And if you don't take anything else away from this webinar, understand that what we are printing is a plastic label. We're putting it in contact with the plastic part, and then we are melting those two materials together, which is why it works. Think of it more as plastic welding than any sort of decorating technology that we previously spoke about. So again, you're taking two thermoplastics and you're melting them together, hence the polymer fusion. We're actually fusing those two materials together. So certainly we are known for our durability. And that's, one of the number one reasons why people come to us is they're looking for that durability for 10 years, 15 years. This is just a really quick snapshot of our test data report. And when you get down into the chemicals section, those are not mists or wipes. We're actually soaking that label material and the base plastic in those chemicals for hours and hours and hours without any sort of degradation. This is accelerated weatherometer testing. In this particular illustration, it is QUV testing specifically, 8 hours of UV followed by 4 hours of condensation. The irradiance factor of the bulbs that are used are up there at the top. Typical time frame is about 2,000 hours for most tests. This is what it looked like at 2,500 continuous hours. Getting into the 4,000 hour range, again, no degradation whatsoever. 6,000. Now you're starting to see the base material start to degrade. And then, of course, at 8,500 hours, total degradation of the base plastic. But it's always interesting to note that it's actually protected in the area where the label is just because of the UV stability of it. So how does this work, right? So what you're looking at here is a traditional hot stamper heat transfer machine. At the top here, you have a heated platen. That platen is running at 550 degrees Fahrenheit. To that, we have mounted a silicone rubber die. We recommend that it be 80 durometer material and then also high temperature silicone. A couple reasons for that. Number one, the lower the durometer, the harder the heat recovery between cycles. It's just the nature of the material. So again, you've got silicone rubber die mounted to a 550 degree heated platen. It comes in contact with the surface of the label and the plastic, and the two melt together. And what you're looking at here is just another method of getting the heat to the surface of the label and the surface of the plastic. Again, here in the back area, surrounded by a red housing, you have a hot plate. That hot plate is running at 450 degrees Fahrenheit. This draping material that is on the outside of the silicone rubber pad has a material in it that can pick up heat, but also deposit heat. So we're picking up the 450 degrees off the surface of this hot plate here, and then indexing it forward and depositing that heat. Polyethylene, polypropylene, it's going to have a melt point, at least at the skin of it, somewhere around 300 Fahrenheit. So it's not going to take very long to melt the skin of the plastic and then also the label itself. So again, that's just another method for getting the heat to the label and to the surface of the plastic. What we're looking at here is SEM analysis, just magnification of showing that the label itself on a molecular level is fused together with the HDPE plastic below. And again, this is going to be applicable to all the polyethylenes and then all, polypropylenes, even the filled materials. So let's talk a little bit about mounting a die. A couple different ways you can go about that. Typically on a heat transfer or a hot stamp machine, you have a dovetail plate that allows you to mount the die to it. You can mount it from the front side with like a die mounting block that we have here, where you're actually going to mount it to the outermost surface, and then that would get slid back into place for the dovetail and then heated up accordingly. You can also use like sheet material. Needs to be a little bit thicker in allowing you to tap the back side of that, but then you can actually mount it from the back side into the die itself. And I think I have a slide of that. Bear with me. Okay, so here we're going through those mounting holes and putting them in the back side of the die. Again, it's just another way to secure it. So you can do it from the front side or the back side itself. Talk a little bit about fixtures, and that kind of leads me to pressure requirements. So with a standard hot stamp or a heat transfer machine, we're looking at about 75 pounds per square inch of force. The mathematical calculation that we use to figure out what the tonnage of a piece of equipment needs to be is we take the height in inches times the width times 75 psi divided by 2000. That gives you the tonnage requirements based on the surface area of your label. And so even though it doesn't take a lot of pressure, you do, when working with a hot stamp or a heat transfer machine, you do need to support the inside wall of that plastic. And so that's what you're seeing here is we've got this little part that's going on the fixture. You'll notice the hole in the fixture, and that is because it fits so tight that when you slide that part onto the fixture, the air that's inside that part needs to go somewhere or evacuate. And so there's a hole straight through the fixture. Again, it doesn't take a lot of force, but it does require 75 pounds per square inch. Let me back up just a little bit too. The other method where we were using the soft pad and picking up heat off the hot plate, that has a pressure requirement of only about 25 psi. So you can do hollow parts as well as curved surfaces. And so again, the pressure requirements are substantially lower on that soft pad situation. Talk a little bit about how to mount the labels on a piece of equipment. Most hot stamp and heat transfer machines come with a 1-inch mounting area. We do have 3-inch cores available or adapters for a 3-inch core. We do print on a 3-inch core. Again, you don't, when you're talking about our plastic label, you don't want to wrap it super tight, but by putting it on a 3-inch core, that allows everything to lay down nicely. So if you need an adapter to go from 1-inch to 3-inch, we do have those available. And then I want to talk a little bit about how to thread it through the machine. Now, different machines have different threading patterns. Couple things to point out. There is a tensioner here. You want to have some tension, but you don't want to have it so tight that the machine is struggling to pull labels and carrier film through the piece of equipment. And so it is kind of a subjective positioning for that tensioning spring. Again, you don't want to have the labels like drooping and sagging. You want everything nice and taut underneath it, and that's where you would adjust this tensioning spring. As you thread a piece of equipment, you want to make sure that everywhere that the label material and the carrier film are touching, you want to make sure that it's touching a roller. You don't want to go over any sort of fixed objects. When you have a fixed object, that's going to cause abrasion and can abrade the label material, which again is raw material. It's a thin layer of plastic. It can abrade that right off of the carrier film. So you always want to be touching a roller. And here's just some examples of it going over a roller. And then that goes to the take-up section, which is a set of pinch rollers where that pulls the carrier film through the material. I want to talk a little bit about photocell registration. Every label that we print has an index mark printed with it. If that's a requirement of your labeling method, we will print an index mark outside of the die area where the die hits in a margin. And that allows the equipment to sense that eye, send a signal to the take-up motor to stop pulling transfers through. That's what's going to allow the label material itself and the die to be aligned with one another. Okay, so that's going to control our left to right. That's photocell registration. And I think I have an example of that here. So here's the index mark. Again, printed outside of the area where the die is going to hit. Typically, we recommend an 1/8 inch die, a die that is an 1/8 inch larger than the image itself. That way you get good coverage, and again, it's going to properly transfer the label material and fuse it into the surface of the plastic. So again, we print an index mark that it gets picked up, in this case, by this photo eye that's right here on the screen. Not sure if you can see my cursor or not, but it's right in line with that yellow mark. Again, that's going to tell the take-up motor to stop pulling transfers through, and that's going to have your left and right alignment. This is just one example of a photo eye. It works off of contrast. And so if you have a light colored index mark and you also have a light colored background behind where the index mark is being pulled through, you may need to change that background. Some of the pieces of equipment have a plate that you can change back and forth between, like a light gray and a black, and that'll give you contrast. I've even gone over to a photocopier and lift up where you put the document and just take a shot of that. It prints you out a black or dark piece of paper. You can slide that paper in. That's just a little secret that you can use. And then if you had a dark mark and a dark background, you can just take a piece of paper and put it in the area between the background and the photo eye itself to get that contrast. So in this particular photo eye that is being shown here on the screen, the magic number, if you will, is the number 5. When you're on the mark and when you're off the mark, it needs to be going above and below that number 5. That is where it's going to send that signal that you've seen the photo eye and stop pulling transfers through. If this was bouncing back and forth between, say, 2 and 3, you're not going above and below that number 5 threshold, it's not going to properly send the signal. So you kind of have to train the photo eye. There is an adjustment here on this photo eye to increase or decrease where that mark is. Here you can see there's a red mark. That indicates that it's been triggered and sent that signal over. Again, if I go back, this is below, no mark, and then above you have the red mark. So again, this is a properly functioning photo eye. It's going to sense that each and every time and align the transfers left and right. And then lastly, I kind of want to talk a little bit about the control panel and some of the functions that may be on your piece of equipment. They're all a little different, but a lot of them have similar capabilities. Um, the things that we're concerned about is time, heat, and pressure. Just like molding, everything's a function of time, heat, and pressure. Well, we are essentially remolding the surface or the skin of that plastic. So the temperature, we're going to set the machine at 550 degrees Fahrenheit. Because we're working with silicone rubber, that's going to allow you to achieve a temperature of 450 degrees Fahrenheit at the die face. So that's where we're going to set our temperature. In this particular case, the temperature setting is in the upper left, and you can turn the heat on and off. Again, we're going to set that temp at 550 degrees Fahrenheit. In this particular still photo, the machine is just warming up, so it's showing 113 right now. But once it's fully hot, we're going to be looking for a number of 550. Also, be careful on your equipment that there isn't any sort of offset for the heat. Sometimes operators will put an offset, maybe 50 degrees or 100 degrees, and that can impact what the surface of the die face actually is. So, a good rule of thumb is when you think it's fully up to temperature, take an infrared gun, shoot the silicone rubber, and get yourself a temperature. You're looking for 450 at the die face in order to properly fuse the plastic label and the plastic part together. The next value I want to take a look at is head up. So a lot of people don't understand what this function is, and it is a time function of how long after stamping, after the dwell time, how long does it take to travel vertically before there's a pause? And this also is impacted by your air pressure going into the regulator on the back of the machine. And so if you turn down your air pressure, it's not going to travel as fast vertically. So you need to be aware of that. The delay itself, we're looking for about a 1/4 inch gap between the label after the dwell, about a 1/4 inch gap, and then we want to pause the machine traveling any more vertically. And we want to pause it for 1 or 2 seconds. And that allows the plastic label and the skin of the plastic part to reach a solid again. We're reaching the melt temperature of these two materials, so you don't want to immediately rip the carrier film off, or sometimes you can have some sticking of that carrier. So by using a delay of a second or two, that allows everything to come back to a solid state and the carrier film to remove easily. So head up, again, is the amount of time it takes to travel vertical before the delay. So we're looking for about a 1/4 inch gap. Depending on what your air pressure is, it's typically about 2/10 of a second. So about a 1/4 of a second of travel vertical before it delays for 1 or 2 seconds. Let's talk a little bit about dwell time, which dwell time is listed on this control panel as well. There isn't a set dwell. There are a lot of things that can impact how long you need to sit on the surface of that plastic in order to get proper fusion. The first one is the part temperature itself. If you have the machine inside a work cell where parts are coming out of say, an injection molding machine and they're warm, they may be 130 degrees Fahrenheit. Well, you're almost halfway to the melt temperature of that material. So decorating a warm part is going to have a much quicker dwell time than, say, pulling a part out of a 50-degree warehouse. You can do it on hot and cold parts, but the dwell time is going to be impacted. And typically, I'm not going to change my temperature setting. I want to leave that as kind of a constant unless I'm working with a material that calls for me to change that temperature. So as a general rule, 550 on the machine, which gives you 450 at the die face, I will typically start with a 2-second dwell, and then I'll work up or down as needed. For example, linear, like low density polyethylene is going to melt a lot quicker than, say, talc filled polypropylene. So when you get into polypropylene, it automatically has a longer dwell time than, say polyethylene. High density polyethylene is going to perform different than low density, and ultra high molecular weight is also going to perform differently. So again, I work with 2 seconds and then adjust up or down as needed. And so with that, when I start at 2 seconds, if everything looks like it's properly fused, I'm going to do a crosshatch tape test. It's ASTM D3359, I believe, which calls for you to uh, do a crosshatch section using like a utility knife where you cut down through the label material into the base plastic, both vertically and horizontally. And then you put a really aggressive tape over the top of that. And that you rub it down really, really tight, and then you rip that tape off. Now, according to the standard, there's a grading scale depending on how much material comes off. So with a polyfuse, though, because it becomes part of the plastic, absolutely nothing should come off on the surface of that tape. If you're getting even just a little bit, there's a problem and it's not properly fused in. So when you think you have a good part, perform the crosshatch tape test, and that's going to help you verify that it truly has fused into the base plastic. So again, time, heat, and pressure, you got head up delay. The difference is head up is how long it's going to travel vertically before it delays. And then for the delay, maybe 1 or 2 seconds to allow everything to solidify. So hopefully that makes sense. Now, I talked about people coming to us for durability. And again, it's going to be there for the life of the plastic. And I would say 90% of what we do is because of branding. People want to have their brand on it, be able to tell consumers who it is, where it came from, and where they can, get another one. So that's a big part of what we do. Track and trace is also very important for a lot of our customers and a big portion of our business where, people are doing uh, like barcodes. For example, this is like a code 39 or code 128, excuse me, barcode. We also see a lot of 2D data matrices, QR codes, and again, we have the ability to do those type of codes, sequential or static, multiples of the same number. Like, for example, if you wanted to do two sides of the part with the same number, no problem. We can create those multiples for you. A lot of people don't understand too that we can work on extruded material where we use the time, heat, and pressure of the extrusion process in order to get the label material fused into the surface of the plastic. And again, this is where we're actually printing in a continuous feed, and then the carrier film is being removed. And so what you would do in this kind of scenario is you would have a take-up section to pull that carrier film off as it gets down to the proper temperature to remove it. And then what happens is that label material then becomes part of the plastic. In this case, it was thermoformed, and again, that's fused into it. Um, just some examples of polymer fusion in an extruded type scenario. Another big part of our business too is safety and warnings. Oftentimes people will have instructional panels or warnings, and that it needs to be there for the life of the plastic to warn a consumer about proper operation or things to avoid. to keep people safe. So again, that is a big part of what we do. And then at the end of the day, because our label material becomes part of the plastic, at the end of its life, it can actually be ground up and made into another piece of plastic that's, polyethylene, for example, and nothing needs to be cut out of it. It is 100% recyclable. And a lot of customers that I talk to, uh, they're designing products right now for end of life in mind. So again, 100% recyclable, nothing that needs to be cut out or removed before it can be recycled. So I really appreciate everybody's time this morning or afternoon or evening, depending on where you're at, for joining me. And again, you can call our office and we will help walk you through this process. This will be available for people to view or come back to right here on LinkedIn. So again, thank you for joining me today. Uh, there again, I don't have a moderator this morning, but I do want to open it up for questions and answers. If anybody has any questions, please give me a call. There's our contact information there on the screen. Anybody here can help you. We even have our my colleague Nick Molden, who is in Europe, available to help with answering any questions. So again, thank you. And I'd like to open it up and see if anybody has any questions. And the way you would do that would just be to put that in the chat section if there's any questions. Some of the questions that commonly come up for myself is, can you deal with different compliances? And absolutely, it can change the palette of colors that we're working with. But for example, some people need to have something that's FDA or CPSIA. And so these are compliances that we can meet. Um, so again, if you have any sort of compliances that we need to address, by all means. Let's see. Question that just came up. Do you need new equipment or can you modify existing equipment? I don't mean to be overly simple on this, but as long as the piece of equipment goes up and down and it gets hot enough, you can do this polymer fusion process. I've actually done it where I've taken a die, put it on a hot plate, pick it up with a pair of pliers, put it down on the surface of the plastic and the label and push down. And again, those two materials will melt together. So I don't mean to be overly simple on that. So to answer the question, absolutely, it can be done on existing equipment. In fact, it doesn't even have to have photocell registration on it. You can use a time pull function. It's not as convenient, and photocell is something that can easily be added to a piece of equipment. This can be done on used equipment, and oftentimes people will contact us and say, "Here's my equipment. Will this work?" And so happy to evaluate that at any time. Let's see, another question. Can the labels be applied to a curved surface like a football helmet? Um, yes and no. It When you start working with compound curves, that can be a challenge because you're curving in two directions. And so it really depends on the overall size of the label material and then also the nature of the curve. And so I recommend to people to take a piece of paper in the size that you want your label to be and lay it on that curved surface itself. If you have any wrinkles in that piece of paper, well, then the carrier film itself is going to wrinkle as well. And so that's going to cause a defect on the part because you'll see that wrinkle. Single curves, not a problem. Like, say, for example, if you're wanting to go around a cylinder, not a problem. Now, as a general rule, you can go about 70 degrees around a cylinder before you start to lose pressure at the outside edges. So you can't go completely around it. Um, I've seen roller type systems, and They just don't get hot enough long enough for a roller system to work. Now, there are peripheral machines where you start with a flat die and then you are rolling the part underneath it. And that seems to work well. And we have had success with that. But again, roller style machines, just in my experience, doesn't get hot enough long enough. Let's see. Do you supply the equipment? No, we do not supply the equipment. We certainly have, partnered with a ton of people that do make the equipment, and happy to give some recommendations there. But we are the label piece of this, and then the equipment. Again, if you're looking at new equipment, we have relationships there and can point you in the right direction. But we do not supply the equipment itself. So, any other questions that may have, you can certainly just type it into the chat window there. Well, I appreciate everybody's time today. Again, this will be available for viewing later. And so, if maybe a colleague of yours, you want to share this with them, that would be great. You can always come back and watch that. It's there for future reference. And then again, if you have any questions or you have a project and you want to talk about it, please give our office a call. Anybody here can help you, and really appreciate everybody's time. So, again, thank you for joining, and we'll see you hopefully next month. Thanks. Bye bye.